All right, 11.2 is on infinite series. A series is what you get when you add up the terms of a sequence. So this is, a sub I is a sequence, and when we add it up, we get a series. So you should have seen sigma notation somewhere before, but just as a reminder, sigma notation, the thing down here tells you where to start, and this up here tells you where to stop. Of course, if it's infinity, then you don't stop. So if you add up just the first n terms of a series, you get the nth partial sum, which is denoted by Sn. So let's look at this series right here. We're adding up 1 over 2 to the n going from 1 to infinity. If we just write out the first 4 terms, the first one we'll get is 1 over 2 to the first power, then 1 over 2 squared, then 1 over 2 cubed, then 1 over 2 to the fourth. And if you add all of that up, it winds up being, I believe, 15 over 16. Yeah, 15 over 16. And we would denote that as S sub 4, because it's the sum of the first 4 terms. And so this thing right here says compute the following partial sums. For this one, the first sum would just be a half. The second partial sum will be a half plus a fourth, which is 3/4. The third one is going to be, add 1/8 onto that, so you get 7/8. Then S4 is 15 over 16. The partial sums themselves, you can think of those as a sequence. And if the sequence of sums converges, then we say that the series converges. So the series that we had in this previous example converges to 1. Now, if that's not obvious to see from what we've got here, let's look at a few more partial sums. If you notice the pattern, the denominator doubles every time. And the numerator is always 1 less than the denominator. That's just for this particular series. So you get 31 over 32, 63 over 64, etc. So you can see that it's getting closer and closer to 1. So this series converges to 1. All right, let's look at a few more and determine if they converge or diverge. So this example 2, number 1 here, I forgot to put the formula in there. So let's just put 1 for my n, or n for my function. Notice down here I'm using n for my index instead of I. It doesn't really matter which variable you use. So this would be the series 1 plus 2 plus 3. Obviously, if you add this up, every time you put another term on, the sum gets bigger. So like, so far, this partial sum is 6, 10, 15, 21, and so on. So this keeps on adding up, adding more and more every time you add another term. So this diverges to infinity. All right, B, -1 to the n. Let's see, when n is 1, this is -1 to the first power. When n is 2, we get -1 squared. So if you think about this, well then, -1 cubed, -1 to the fourth, and so on. What you get here is -1 plus 1, -1 plus 1. So the partial sums are, let's see, the first one is -1. The next partial sum is 0. The next one is -1. The next one is 0. We're getting that by adding all these up. So they're not converging to anything. The partial sums are jumping back and forth between 0 and -1. So this diverges. It doesn't diverge to infinity, but it still diverges. All right, this one, if our formula here is just 2. So that means when n equals 1, we've got 2. N equals 2, we get 2. So we're looking at what we get when we add up an infinite number of 2's. That's obviously infinity, so this thing diverges. All right, D, 1 over n factorial. Remember, n factorial grows really fast. So if we start doing these, the first term is going to be 1 over 1 factorial. And beneath that, I'm going to write what this is. That's 1 over 1. 1 over 2 factorial. 2 factorial is just 2. 3 factorial is 6. 4 factorial is 24. Run out of space. So the numbers we're adding up here, the terms themselves are shrinking to 0 very fast. And although I'm not really giving you a good explanation for it yet, this is going to, I shouldn't say equals, this is going to converge. To what? Well, we'll see that later. All right, let's look at these on example 3. Let's see, this is 1 plus a half plus a third plus a fourth. It's not obvious at all. I'm just going to tell you this one diverges. This one right here would be 1 plus a fourth plus a ninth plus a 16th. Again, this one's not obvious at all, but it converges. This one over here, this one is going to diverge. Now, the reasoning behind these three is actually exactly the same as the reasoning for improper integrals, which we just talked about, we talked about in section 7.8. I just wanted to mention these three now. We'll come back to these later. These are actually what are called P-series. Now, number 4 here, I want to look at. I think we can look at this one and figure it out. The first number in this would be a half, because 1 over 1 plus 1. The next one would be 2 over 3. 3 over 4. 4 over 5. Well, notice what's going on here. Eventually, if you're doing this, you'd be adding up 100 over 101. 1,000 and 1,000 over 1,001. So as n grows large, the numbers that you're adding on to here, the terms are approaching 1. So that means that the sum, if we keep adding 1 onto it repeatedly, or something that's essentially 1 repeatedly, the sum is going to diverge to infinity. So the main questions for this section are, if you're given a series, does it converge or diverge? And if it converges, what is the sum? Well, this example right here, number 4 that we just did, gives us one sort of clue here. In order for the series to converge, the terms have to shrink to 0. And the other thing is they have to do it quickly. Now, the big question here with my beautiful cartoon is how quickly do they have to shrink? And that's not an easy question to answer. It's going to take a good chunk of chapter 11 to answer that.